Hello class and welcome. We will be starting week 10 material and the chapter is chapter 5 in the microelectronics textbook. So the last sessions last week we covered chapter 6 BJTs, and so today we are actually going one step backwards in the textbook, but I think this is the right way to progress, move ahead. So anyway, no big deal. Either way it should work, even according to the textbook itself. So the topic that we'll cover this week is what's called MOSFETs, or metal oxide semiconductor field effect transistors. So it's a big name. The previous type of transistors we saw were BJTs, or bipolar junction transistors. These are MOSFETs, or metal oxide semiconductor field effect transistors. Now, transistors basically have two primary functions. You may be aware of this. I may have mentioned it, hopefully, or not. But either they act as amplifiers or they act as switches. Right? For analog circuits, the amplification property is important, and for digital circuits, the switching on and off property is important. So these MOSFETs, similar to BJTs, also possess a lot of the same characteristics. In fact, if you look at the two chapters, chapter 5 and chapter 6 in the textbook, the material is almost similar to each other. Every page you can compare, and what the writer is writing, you can see that there's so much commonality between the BJT and the MOSFET. So hopefully this will be easier to follow, because we already did the BJTs, and in my personal opinion it's a little bit easier to understand MOSFETs anyway, because their operating principles are slightly easier than BJTs. So hopefully you will feel the same way, just because of the natural simplicity of MOSFETs, but also because we have already seen all of the basic ideas in the previous chapter, and so you should recognize that in this chapter we are kind of repeating the same concepts. Okay, there are differences, don't get me wrong. There are definitely plenty of differences in basic operating principle, etc. But nevertheless, they are both semiconductor devices. They are both supposed to achieve the same goal. So that's why they are similar, but with differences. Okay, so having said that, let me move ahead. One thing I should have done before, which I haven't, is to put slide numbers so that we can see which slide we are on. So slide 1, the title slide. Let me move ahead to slide 2, where I list all of the topics or sections in the textbook in this chapter 5. So as you will notice, there's the first 5 topics in dark font, and then the next 4 in lighter font, and that is to tell you that we are only covering the first 5 topics in this class, meaning in EE 280 we only do the first 5. Exactly the same thing we did with BJTs, only the first 5 are necessary to be covered, and the remaining 4 are, I'm going to leave it up to the next class that you'll take on this topic, EE 380, and for that professor to cover. So this is how we do it generally at NAU, and I'm following the same model here also. Okay, all right, so we still have 5 sections to cover, 1, 2, 3, 4, 5. And what I'll do is I'll split my material, my recordings, into 4 sessions. Yeah, 4. So I will cover 1, 2, 3 lecture only right now in this recording. So sections 5.1, 5.2, 5.3, we'll do it now. I'll cover the lecture portion, and then we'll solve problems in the next recording. and then I'll do the same thing with 2 more recordings for sections 4 and 5. Okay, this is again what we did for the BJT also. Alright, so the first thing is to understand the device operation or device structure and physical operation of MOSFETs. So let's move ahead to slide 3. As you can see, there's a lot of subtopics within the main topic 5.1. So 5.1 to 5.11 to 5.19. Alright, most of these are similar or parallel to the BJT. There's maybe one or two slightly different, but anyway, we'll cover all of these quickly. Okay, so moving to slide 4 on the PPT is the first main slide with some material. And this is a good illustration. This is from another textbook, not from ours, but I think it helps to understand what exactly a MOSFET is all about. So starting with the picture to the left, label A, if you take an insulating material, which is what you see in the top middle there, and put a plate on the top, a conducting plate, and a p-type silicon on the bottom, you created a kind of a you've got all three, right? You've got insulation, conductor, and semiconductor. So to that structure, if you apply a voltage in that one direction, that means between the semiconductor material and the conducting plate, if you apply a voltage, you actually observe a capacitor in operation. That means charge begins to accumulate on the top plate and the bottom plates, and the semiconductor material or the insulating material, the dielectric, prevents current from flowing, right? This is basic capacitance theory, and I hope you remember that. Now, to this, if you apply a voltage in the other direction, right? So in one direction you have this V1, which helped to create that charge and make the whole thing behave as a capacitor. But now in the other direction, perpendicular direction, if you apply another voltage, then electrons start to flow and current starts to appear. Okay, so that is the core behavior that defines an FET, a FET. So let's move on to the next slide to see a little more in the way of details. And this material now is from our textbook, so you should find it also in your textbook. So you can see that the insulating material in the middle, which is so important to create this capacitor. Now this doesn't look too much like a capacitor. The capacitance model was only to help to understand the logic, but in a real world, this is what a MOSFET looks like. And again, this is a simplified structure. And so what you see here is that insulator is created using silicon dioxide. Okay, so that silicon dioxide is sitting on a big wafer of p-type semiconductor material. Okay, and the gate G is actually that conductor. So you have the conductor, you have the insulator, and you have the semiconducting material. Now, in addition to this p-type body, which also, by the way, has a terminal but is generally not too important in most applications, we just ignore it. But this p-type body, that means it's semiconductor silicon doped heavily with holes, right, with p-types, acceptor doping. Also has these two little parts of n-type doping. Okay, so these are donor type doping. So, and one of these we call it source, which is on the left side, the other we call it drain. And the source and the drain are n plus, they are heavily n-type, and they have conducting leads that are brought out, terminals S and D. So, and then another important factor is this channel length L. Okay, in this drawing you see channel length, but you also see channel width W. So W and L are both important Remember them, we'll use them later. But this is what it looks like from the side, from the isometric view. Okay. So this is a structural display of NMOS transistor. This is N-type MOSFET. So as you can imagine, there's going to be a P-type MOSFET also. Similar to your NPN transistor and PNP transistor, we have these NMOS transistors and PMOS transistors. Okay, NMOS FETs and PMOS FETs is the right way to say it. Okay, so first of all, since we got this terminal out, the gate terminal, we have to start thinking about applying voltages, right? Because remember, in slide 4 we said you need two types of voltages to have the FET to actually operate and give us some benefit. So first of all, let's talk only about the voltage at the gate. The gate is that portion of this block which creates the capacitance. Okay, remember that. Then the drain and the source are the other two terminals between which we want the electrons to start flowing. But to create the charge, you first have to apply a voltage to the gate. Okay, so with zero gate voltage, basically two back-to-back diodes exist in series between the drain and the source, and you can see how there's two back-to-back diodes. And the path between the drain and the source has a very high resistance, so nothing really happens. Nothing is flowing. Next slide, slide 7, is where you see we start to create a channel for current to flow by applying a voltage at the gate terminal. So now if you put a positive end of the battery to this gate and leave the other two open still, it is shown as a circuit symbol here. I know it's too early to talk about circuits and symbols, but I just had to bring that that graphic in. But ignore this for the moment and just look at the voltage on the gate. So as soon as you apply that positive voltage, what happens is you create a depletion region full of negative ions here. Okay, and so in the graphic to the right, bottom right, you see that there are free electrons that are created, and once you have free electrons, that's because negative ions exist, right? You pull an electron out of a neutral atom, then you get an ion and you get that free electron. So there's a channel of free electrons and then there's a whole bunch of negative ions, and all this is sitting on that P substrate or P body with N-type, these buckets. Okay, so this is the first step in making all this work. So let's move to slide 8, and this is from our textbook, this graphic. So the same thing is repeated, but with a little more detail. So you see the same picture, and what you see is this white region that has been created as soon as you apply that gate voltage. Now the gate voltage is with respect to ground. So source and drain, the other two terminals, are grounded, and the gate has a positive voltage. The body is also grounded. So if you do this, then you can see that a depletion region is created, and then an induced N-type channel is also created, right? So these two things are new. These didn't exist before you put the voltage on the gate. So these two things, an induced N-type channel and a depletion region, are created. Okay, let's move on to slide 9 now. On slide 9, now not only have we are holding that gate voltage, the positive voltage, we are now applying a small drain to source voltage. Okay, the voltage appears here. The source is still grounded, right? But with respect to this ground, this drain, we apply another voltage. Okay, so we got two voltages, one on the gate and one on the drain. Now we'll see what happens. Here's the bullet points that tell you physically what's going to happen. An induced or inverted channel is created due to VGS, right? That we already saw. The applied voltage VDS, this voltage, causes a current ID to flow through the induced N channel. since the voltage causes current flow, the current ID is a drift current. Okay, remember drift and diffusion, right? There's two different types of currents. In the BJT, we said most of the current is due to diffusion. Here, we say that most of the current is drift current because of the applied voltages. The magnitude of VGS determines how large ID will be. So, this gate to source current or voltage actually determines the magnitude of ID by and large. Okay. Current is carried by free electrons traveling from source to drain. So the current is actually because of free electrons going in that direction. I put this red arrow electron flow to tell you that electrons in an NMOS type device, they're actually flowing from source to drain. Okay. And remember, normally we take the flow of current in a circuit to be from the positive to the negative, right? Which is opposite to the flow of electrons, which are always from negative to positive. So basically, the external current ID, which is also shown in this direction, is opposite to the electron flow. Okay, so that's the last point. Since the direction of current flow is opposite to that of the flow of negative charge, the current in the channel ID is shown as from drain. It is shown as from drain to source, but actually the electrons are flowing from source to drain. Okay. All right. Now that we have a current flowing, well, we need to know what the magnitude is, right? How much current? Can you tell me? That's the question. So we have to start deriving a formula for that drain current. So there's a lot of new terminology that will come even in this chapter. I know even in the BJTs we had plenty of new terms that you guys learned. Many of those will be repeated, and we'll definitely have a few more new terms. So, I mean, we already learned source and drain, right? Those were different from emitter and collector in the BJT. So, expect to have another half a dozen important words that you'll have to start to remember. First and foremost is something called overdrive voltage. It's generally shown as VOV. Okay. What is overdrive voltage? It is VGS minus something called VT. So that's the definition of overdrive voltage. Now VGS is just this voltage, right? The gate to source voltage that actually helps to create the charge and begin the fun, right? So what is VT? VT is a new term. VT, remember we already had a VT in the past, right? So don't confuse that VT. That was something called V thermal, which we used a lot in BJTs, and it had a value of 25 or 26 millivolts, a constant. Here we have something called VT, also VT, or sometimes in some textbooks you see VTH. And the real name of this is threshold voltage, and it's generally between 0.3 volts to about 1 volt. This voltage is actually more like the cut-in voltage of a PN diode. You remember the cut-in voltage, right? As you put positive bias on a PN junction or a PN diode, you have to go past a certain value, right? 0.5, 0.4, 0.5 for the diode to begin conducting even with positive polarity, right? Positive bias. So the same thing, so something similar. It's not exactly the same, but something similar. But remember, this VT is going to appear quite a lot, and it will sometimes have this TH, but it has this value roughly. In problems, we are generally given that. Okay, so moving past, we have another complex equation for the current, right? Remember, for BJTs we had something called IC, right? I collector current, and that had an exponential relationship to the base emitter voltage, right? So something similar here, but it's not an exponential relationship yet. In fact, it will turn out to be a square relationship. So hold on until we get there. But for now, for understand this logic, the I drain depends on these voltages. It depends a little bit on VGS, which is this voltage. It also depends on VDS, this voltage. and there's a whole bunch of other parameters, all from the physics of the semiconductor material. Okay, so you have this electron mobility, right? Mu n. You may remember this. We studied this in the first chapter on semiconductors. Then there's something called COX, also called oxide capacitance. It's actually capacitive density. It's not in farads, but it's farads per meter square. So this is another factor that appears in the formula. Then width by length, right? We already saw length of the channel and the width of the semiconductor block. So this is called the aspect ratio, W by L. This is just a physical measurement of the size of this block of silicon. So that appears, and then we have this VGS minus VT, which also we call overdrive voltage, VOV, is in the formula, right? So the current depends on all these. These are pretty much constant. The only thing that even Vt is a constant. So VGS and VDS are the only two variables, and so we can write ID equals a certain constant times VDS. This constant still depends a little bit on this, but it's still, this is easier to understand, right? Current equals voltage by something, and this something is called transconductance, which is the opposite of resistance, right? So I equals V by R. You can relate it to Ohm's law. So what is this transconductance GDS? I define the oxide capacitance, that is also generally a constant value. So GDS has three factors: this, and this. This is a constant, this depends on the size, and then this voltage over drive voltage. So the three of those defines the GDS, and it's also written generally as Kn times VOV. Kn, unfortunately, depends on another Kn bar. So all these are new, and you have to get familiar with them. So this Kn bar is called, or Kn prime is called, process transconductance parameter. Kn is called transistor transconductance parameter, and we'll use all these in some simple problems to understand how they all fit together and what their magnitudes are. How big are they? Are they 10 to the power 15, 10 to the power minus 15? The size of them. All that goes to help us create this formula for the current, the drain current, which is the current flowing through the device. Okay, so become familiar with this form. GDS has this simpler form, Kn times VOV. VOV is just the difference between the gate biasing voltage minus a fixed voltage called the threshold voltage. Okay. Alright, we'll come back, we'll solve problems, you'll become more familiar, so don't be too worried yet. I'm moving on to slide 11. So far, all we have done, we are still continuing with applying a small voltage, right? So the small VDS is roughly 50 millivolts or lower, right, in that region. So what these graphs show you is, for different values of VGS, right, you have different slopes, and that slope is this transconductance. Okay, slope is generally 1 by R, right? In most Ohm's law formulas and graphs, you have seen that a slope gives you the connection between current and voltage. The same thing here, and the slope, but the slope also depends on the magnitude of VGS. How high is it compared to that fixed VT, right? And based on that, you can draw these four, curves or straight line graphs. So linear resistance, often in this region where VDS is very low, small, we can think of the MOSFET as a resistor, and that's what you see in the red here. The MOSFET acts as a voltage dependent resistor if the gate voltage exceeds VT. So remember, first of all, while VDS has to be small, it has to exceed VT, which is 0.3 to 0.1, whatever. Of course, if this is 1, then VDS has to be above 1, but assuming it's at the lower limit, 0.3 or something, then 50 millivolts will give you slightly above that voltage, right? And so as long as this condition is satisfied, that the gate voltage, hold on one sec. Yeah, we are talking about drain to source voltage being small. Sorry, not gate to source. Okay, my bad. So all this is for obviously with a small VDS. I mean, these relationships are still all valid, but a small VDS. So apply a small VDS, and if the gate voltage VGS exceeds VT, then you can model the transistor, the MOSFET, as a voltage dependent resistor. And so RDS is defined as 1 by GDS, and IDS can be written as VDS by RDS. Okay, so these are just relationships to help you become a little more comfortable and to model a MOSFET in this region where VDS, the drain to source voltage, is small. Okay, so this MOSFET, if you think of it as a resistance only, it depends on these three factors again, these three that I showed you in the previous formula. So those three same factors also say how small or how big will that resistance be. It depends a little bit on VOD, that means it depends on VGS, the gate to source. So that's why we call it a voltage dependent resistor. Okay, I'm going to move on to slide 12. Now we are starting to increase VDS. Okay, so the previous slides were about VDS being small, about 50 millivolts. So slowly, as you increase, what's going to happen? That is the interesting portion next. So what you see is this channel, which previously we showed it as a just a straight line, is now taking on a certain profile, right? It's starting to become more triangular rather than rectangular that it was previously. I don't know if you had here you see it was just a rectangular or parallel channel. That channel, as you increase this voltage, is starting to take a shape of a triangular form. Okay, so as VDS is slowly increased, now things again start to become interesting. And so what is this graph showing? So first, remember, we are only increasing VDS, so keep VGS constant and make sure it's greater than that threshold voltage, okay, VT. So as long as VGS is VT plus some overdrive voltage, and you slowly start to increase the value of that voltage, as long as VDS stays below V overdrive, right? So let's assume that VGS is like, let's say 5 and VT is 1. So V overdrive is 4, right? So you can increase VDS, but it has to be less than 4. And then this graph applies. So as long as the VDS is kept under VOV, this profile is what you see, and the channel also begins to look like this. Okay, so it is wider at the source and narrower at the drain, and this X tells you the distance going from the source towards the drain. Okay, so this average is just the half of this value, right? Half of this height gives you the average value. So we define an average here, okay? And this is the VDS and this is the VGD. I don't want you to get confused with VGD, so let's hold off on that. But this is what happens as you start to increase VDS, as long as you keep it below VOV, okay? So this is how the current changes as you slowly increase the VDS. Again, staying below the over voltage, the VOV, okay? And this portion is called the triode region. The curve actually is parabolic. It's not really exponential, which would have been like that. It's called parabolic because you have a square relationship. So the current is related to this VDS in a square way with a second power, and this is the formula. This is similar to what we just saw previously, but we write it in this way to show the square effect. Okay. All right. So there's two variations of this. One of them writes it with a VOV, the other writes it with a VGS minus VT. Okay. I'm using capital T, which may be confusing to you. So because different books use different things, so let's just change it to small t to stay consistent with this textbook. Okay. Now what happens as VDS goes even higher? Now we are allowing it to reach VOV and even grow above it. Okay. So VGS is still constant, but it's greater than VT, same relationship, and now VDS is raised to VOV first and then above. Okay. So now you see what is happening to the channel, right? Previously the channel it stopped at a certain height. Now that height on the drain side is zero, and this channel is called pinched off, and the VDS slowly increases up to the maximum. In this case we stop at VOV. Okay. Then what happens to the remainder? That becomes VT, but we'll come to that later. Okay, so you can see this. Now here's an interesting graph that again tells us what is happening to the current depending on how you increase the voltage. So as the voltage on the drain is increasing, we saw this region called the triode region. Now we enter something called the saturation region. And remember, this is VDS. So we started slowly, kept it low, 50 millivolts or something, then reached VOV, which may be 3 or 4 volts, and then we went even beyond. But there's no point in going beyond, because what happens is the drain current ID flattens out. It saturates and it just stays constant. So VDS is raised to VOV, ID reaches saturation. Okay. At saturation, we are interested in what is the current, and so the drain current is shown to be ID times half this, and it's still a square relationship, but we substitute VOV because that's where the effective voltage stops. Even though we are applying more and more drain voltage, the current actually only requires us to know the over voltage, the VOV, and that's where it stops. So the desaturation is that VOV, right? The more voltage you apply, it doesn't really impact the current anymore. You can keep applying, it's not a problem, but for purposes of calculating the current, you only need to know the VOV. Okay. So all these equations again are derived in the chapter. We can spend a lot of time trying to understand them. They are not too important if we are trying to understand how to use this in a circuit and create amplifiers. It's useful to know the physics, to have some general idea, but the exact calculations I feel aren't important. But if you guys are interested, certainly read the textbook and become familiar with the methods they use to actually come up with these currents. Okay, a lot of it depends on the charge, right? Remember, this is basically a capacitor, right? So, but you're making the electrons move in a different direction, in a perpendicular direction. So there are these fields and the charge, and all this comes into play to help us derive a formula for the current. So I'm just showing you the final formulas. I'm not spending too much time on the derivation, but I encourage those of you who are interested, who have the time, to read through it. Okay, that was slide 16. I'm going to move quickly to slide 17. I know we are always running short on time because these chapters are packed with lots and lots of information and we have plenty to cover. So excuse me if I feel like I'm rushing. But I did want to spend a few minutes comparing what we have already learned about an NPN transistor and this NMOS FET that we are studying now. You'll be surprised to see that this definition of saturation is pretty opposite. Well, the definition is kind of similar because something stops growing, right? In this case, we say IC stops increasing even as you keep changing VCB in an NPN transistor. For a FET, we are saying the drain current stops increasing even if you keep increasing VDS. So in that sense, they are both similar. But what we call active mode in a transistor, in a BJT, and use it for amplifier design is really what's called saturation in FET and used for amplifier design. And what we call triode here is what we call saturation here. So it's a little bit opposite, so I hope you're not confused, but definitely I want to warn you to be careful. Saturation in NPN means something else, and in FET it means something else for when we start to actually use to design amplifiers and so on. Okay, so that's one slide I put together. Another one I have is also full of differences between a bipolar transistor and MOS devices. I won't have time to go through all this. I request you to read through it. You'll understand because we've done BJTs pretty well now. But there are a lot of similarities but lots of differences also. So this slide kind of summarizes the two. Okay. Alright, so at this point on slide 19, I introduce an example from the textbook, but again I'm not addressing examples and problems in this recording, so we'll come back in the next recording. But just to see what the questions are, you would expect, right? We've come up with a formula for drain current, so we're going to be asked what is that drain current. We also had a formula for transconductance, that resistance, so you can expect that we will be asked to use all of those. And then there is the overdrive voltage, right? And then the formula that connects the current ID to the gate to source voltage or the drain to source voltage, and we also defined saturation. So all those we'll have to use to solve some of these problems. But we'll wait. I have one problem. I have another problem from the back of the chapter 513. We'll wait to do that. We have a few more things just on the theory, so I hope I can finish that in the next 10 to 12 minutes. So section 5. We are still on 5.1, by the way. 5.1.7, the textbook introduces the PMOS transistor, right? So this is a variation on this is different from the NMOS. It's still a MOSFET, but here you notice everything is opposite. In the NMOS, we were sitting on a big chunk of p-type body, p-type substrate with two buckets of n-type. Here it's the opposite. For the PMOS, we have two p buckets sitting in a big chunk of n-type semiconductor, silicon, but we still have the gate and we have this insulating material which is silicon dioxide. Now, the channel that is induced is always, it's called an inverted channel because the channel that's induced when you apply a voltage is always the opposite of what's the body type, right? So if the body type is n-type, you get a p-type channel. That means the flow here is all p-type material or holes. Okay. Also notice that the V gate to source voltage is negative in this case, right? Previously for NMOS we made that positive, while here it's negative. Similarly, the drain to source voltage is also negative. So this is the opposite of what you see for the NMOS. So to summarize, a negative gate voltage VGS creates an induced P channel. To cause a current ID to flow in the P channel, a negative voltage VDS is applied to the drain. So when we say negative, it's because this is all with respect to the source, which is grounded. So with respect to this ground, this is negative, this is negative. Okay. The current ID is carried by holes. Okay. Previously in NMOS, we knew that the current ID was primarily because of the flow of electrons from the source to the drain. For a PMOS FET, the current is carried by holes and flows through the channel, through this channel, from the source to the drain. So it's still flowing like this, and we show the external current in the same direction because this is all positive charge flow, right? Positive flow. So the directions you should watch out, they can be reversed for a PMOS. A couple of other factors. We remember the factors K, Kn and Kn prime. For a PMOS, we introduce Kp and Kp prime as those parameters that will help us, come up with the formula for the current. And then this other important factor called hole mobility, right? Previously we talked about electron mobility, that was the mu n. Here we talk about mu p, and one of the important facts to remember is that the hole mobility is only about 25% of so I guess just to avoid confusion, I should say 2. Yeah, 2, not tau. Oops. Yeah. So it's only a quarter of the value of an electron mobility. So basically what this is, holes cannot move so well as electrons can. In a PMOS, everything is a little more difficult compared to an NMOS because electrons naturally tend to move faster and holes only move, their mobility is only a quarter to half. So this is a fact that is useful for later on when we look at combined NMOS plus CMOS plus PMOS circuits. Those are called CMOS, complementary MOS, but we'll wait to get there. But just remember, this is an interesting fact, okay, about the hole mobility and electron mobility. Okay, I'm going to move to slide 22. Yeah, you see CMOS, right? CMOS is a combination of NMOS and PMOS on one silicon wafer. So you have a p-type body, so you create an NMOS, then you create a well of N material, and then you create two little buckets of P. You put it all together, you have what's called a CMOS, and CMOS is the most important technology in semiconductors today, right? So just an introduction, we'll look at this in some detail. Definitely next chapter, we jump to actually chapter 13 in the textbook, is all about CMOS, but we'll wait and do more of it then. But this is a picture I hope you can appreciate what CMOS is all about. Okay. Now finally we come to section 4.2 where we have to look at certain current voltage characteristics. You may remember when we studied BJTs, we had a section 6.2, exactly the same topics, circuit symbols, some relationships between current and voltage across the drain or drain to source voltage and gate to source current or gate to source voltage, and then a few other factors. So let's move on. Slide 24, we introduce some symbols. This C is the only one that we'll use a lot. So the others were how C came about. I'll leave it to you to read it in the textbook, but only remember this C is pretty important. Here is a summary of everything. It's in table 5.1 that we already studied. Nothing new, but it's a good summary of all the various stuff that we have covered so far. The circuit drawing, the graph, the triode region, the saturation region, the definition of the over voltage and the thermal, the threshold voltage, etc., etc. Okay. Okay. So we look at something called ID versus VDS characteristic. Really, there's nothing new here because we have covered most of this already, right, in the previous sections. So I can actually skip this for quickly. This is for one fixed gate to source. So you fix gate to source voltage VGS, and then you vary VDS first up to the over voltage limit, and then you go past the over voltage and you come into saturation. Okay. Alright, so now maybe this is a new graph for you to understand. So if you take different VGS level, so first take a VGS level 1, right, let's say 4 volts, plot your graph for ID versus VDS, then shift the VGS to the next level, maybe add 0.5 volts to it, so you went from 4 to 4.5. Then do the same thing. Then go to a higher level for VGS, maybe 5 volts, do the same thing. So if you collected all these together, you have this collection of graphs, and this becomes important as we go to the next slide and the next slides, where we start to now plot I drain versus VGS. Okay, so assuming VDS is fixed and it is a certain value, VDS has to be greater than that, remember that over voltage value. So as long as we are above that, which means we are in saturation, right, this is the shape of the relationship between VGS and ID. How does ID vary with variation in gate to source value? So previously we kept the gate to source voltage constant and varied the drain to source. Now we keep the drain to source constant above a certain level in saturation, and then we vary the gate to source. So this is one of the most important relationships. That's why I put it in red. It's the main relationship to understand MOSFET amplifier behavior. So we haven't come there yet, but I thought I'd bring it in and show it to you so you start to remember the importance of it. It is shown in this case as with VGS minus VTN, that N came in because now we know both NMOS and PMOS, right? So we have to differentiate whether we are talking about NMOS or PMOS. But this relationship, we can put this as VOV actually also, or VDS saturation squared, but this relationship is important. Conclusion: in the saturation region, the MOSFET operates as a constant current source where the value of the current ID is determined by VGS as per this formula. It's a square relationship, a parabolic relationship, but remember this is the relationship. Okay. Here is a model, and you're familiar with models. I actually showed you for comparison purposes. I brought in the NPN BJT model, which we did previously, but the big one is the new model for the MOSFET, and this is an NMOS. So basically you have a current source, it's a dependent current source. What does it depend on? It depends on this VGS, this voltage. Okay, so that's how you model. But this is a large signal, so we'll do small signal later, but all the relationships are here on this slide. Okay, moving on to slide 30. I just brought in a couple of circuits because you will, as you start looking at problems, this is what the whole thing will look like. You will not have those blocks of N and P shown anymore. We're going to start using circuits, and by now, because we have done BJTs, you're comfortable with the idea, so I just brought these in to show you. Okay, moving on, slide 31, we have a problem, so we'll wait to do that. Next slide, 32 is an example, we'll wait to do that. 33, we'll wait to do that. 34. Okay, So we come to a few additional details. So give me another 5 minutes. I know we are running late, but I want to finish this in one topic. It should be over in another 5. Okay. So remember the early effect when we were studying BJTs, we realized that what they've been telling us, that the collector current doesn't depend on the collector voltage anymore. Then they said, oh yeah, it does depend a little bit, and that little variation is because of something called early effect. Similar to that, we have something called channel length modulation in MOSFETs also. Okay, so what happens is that channel which we were used to draw until the very end, it starts to shrink as you keep increasing the drain to source voltage, the VDS. If it keeps going above saturation, then it is causing an effect. The effect is small, it's not too large, too important. In fact, most of the problems in the textbook, we're going to ignore it. But you must remember that if the original formula for the current is like this, the new formula to include the impact is like this. So this new factor 1 plus delta VDS comes in. This delta, is that delta, or I don't know what, I have to remember what it is. Let's call it delta for now. So this delta is a device parameter having the units of reciprocal volts, okay? And a small signal output resistance. We haven't done small signal models yet, so hold off. But we have seen a large signal model, right? So the small signal resistance comes out in parallel with this regular model. So you have to introduce a new resistor to account for this effect. Okay. So this effect is similar to the early effect for BJTs, and this can be, if you run into a problem where they say, okay, now do include the early effect or the channel length modulation, then they'll give you this lambda. I think this is the lambda. So they give you this lambda, and then you have to include that in solving the problem. Okay, but the physical explanation is like this. Okay, so I won't waste too much more time on that. Let me move to slide 36. Slide 36, we bring the circuit symbol for a MOSFET, and you'll see that for a MOSFET, similar to for a PNP BJT, the arrow points inwards. Previously for an NMOSFET, it was pointing outwards, so that's one of the differences. So remember this symbol. Then we have a problem with okay, well, we came to the final section, and this section 5.3, the final section of this recording, we don't really have much in the way of theory. We jump straight into problems, and there's actually a lot of problems. I think there's 6 or 7 problems that are solved. They're actually examples in the textbook, and I will do a couple, example 5.3, 5.8, and maybe one problem from the back. But I do encourage you to look at all the problems. And this section is basically about using everything we learned so far to actually come up with some biasing conditions. Now, we haven't talked too much about a Q point and a bias condition and DC operation yet. We'll do that as soon as we begin the next section on amplifiers. But the real reason that we have this section is to help us answer the question, if I know I want a certain combination of the voltage gate to source and the current ID, what resistors, etc., and what voltages do I need to get started, to create a circuit so that I meet that condition of having a certain bias condition, which means a certain voltage plus current combination. Okay, so if you look at any of these, you'll be asked to answer, determine the values of the resistances RD and RS so that the transistor operates at a certain drain current 0.4 milliamps and a certain voltage VD, which means this voltage, which basically really means the drain to source voltage, right? So that's my point. So the question is always to help us find those conditions, and that is what this section is all about. MOSFET circuits at DC. It's full of problems, so we'll wait to do this in my next recording. Okay? Sorry for being slightly over time, but I hope this was helpful. And if you have any questions, of course, you can always approach me. Okay, thanks. Bye.